Okay, YouTube, in this video we're going to be exploring the distance formula. And so as we continue to analyze graphs in the xy coordinate plane, we'll often want to find the distance between 2 point values. And so we're going to start by introducing again the Pythagorean theorem, but then kind of build on how that leads us to the distance formula. So let's go ahead and review the Pythagorean theorem. It states that if we have a right triangle, okay, A, B, and C, where C is the hypotenuse, then it is always the case that the sum of the squares of the legs of the triangle, okay, leg, the sum of those squares must be the square of the hypotenuse of the triangle, the longest side there, if it's a right triangle. So that being said, that relationship we use so often is really helpful when we want to find the distance between 2 points. So let's suppose we would like to find the distance between 2 points. And so what I'm going to point out here are a couple of points in this image, but you can see that we have a point x1, y1 that occurs to the left of some point, and we're calling this point here x2, y2. And so the important thing to note is that if we're going to find the distance between these two, and we can always connect these right here, is that we can always kind of create a right triangle out of this situation. So the neat thing about it is essentially this. Since we know the coordinates of both the first point, and the second point, then if we wanted to find, say, the base of this triangle right here, because we know the x value of the first point and we know the x value of the second point, then the distance between these 2 points right here is the absolute value of their difference. So the distance and the difference are very much the same thing, and we're going to write a note here as always positive. Not that it matters because we're going to square things, but it's kind of always positive here. So we say this is the distance with respect to x here, the base of our triangle. If we wanted to find the change in the y values here, you can see that we have y2 minus y1 here would give us the difference between these two y values, or the distance on this side of the triangle. So the neat thing about this is that we can take our Pythagorean theorem here that says that these are the two legs. When you square them and add them together, then you're going to get the square of the hypotenuse. And we could say that, well, the bottom leg here really was the change in the x values here. So we have x2 minus x1 squared plus y2 minus y1, the change in our y value squared. This should be equal to what I'm going to call as the distance here, d squared. And so this leads us really to the distance formula. And the distance formula is nothing more than what you see here, except for that the distance formula we solve for d. So if I solve for d in this expression right here, that would involve taking the square root of both sides. But what we wind up with is this distance formula right here that says, look, if you want to find the distance between 2 points, and these points are defined as x1, y1, and x2, y2, which is a first point and a second point, then what we're going to do is take the square root of the squares of the differences here in x and y summed together. Or in other words, we're going to use the Pythagorean theorem. So let's go ahead and do this. I want to give this a shot here. And what we'll do is this. I ask us to find the following distances using the distance formula and using the points that we gave in example 1. So we want to support ourselves graphically as well as algebraically. So in my first example here, I said between point A and the origin. Well, in my first example, I used the point A as 2, 3, and that's this point right here. So what I'm going to do is I'm going to go ahead and sketch an A. A is 2, 3. As a matter of fact, I'm even going to label this 2, 3. And I'm going to find the distance between it and the origin, which I'll just call O, which has coordinates 0, 0. And so something I want to say about this here, 0, 0, this distance here, graphically, it's very easy to look at this as just a right triangle. And I would really encourage you to set this up as a right triangle, because what you see here is we just have those distances that you see right there, 2 and 3. So one might make the argument, can't I just go ahead and say 2 squared plus 3 squared? That's our distance squared here. And I would actually come back and say that absolutely you can do that. So what we get here is we get 4 plus 9 equals d squared. In other words, we get 13 as our d squared. So solving for d now, we actually get the square root of 13, which is plus or minus, but we say keeping only the positive because we're talking about a distance here. Now, in terms of what I asked us to do, I wanted to use the distance formula to do this. So in terms of our 2 points, we're going to write these out here. We say one point is 2, 3, and our other point is 0, 0. And so we have an x1 and a y1, and we have an x2 and a y2. So according to our distance formula, then really what we can do is just get ourselves set up here with these two differences. And what we'll do is we'll take the difference in our x values, which are 2 minus 0. Let's say I do 2 minus 0. So I did my x1 minus x2 this time. Let's do y1 minus y2, and we'll get 3 minus 0 here. And so what I want you to see is that this really just essentially simplifies down into the same expression here where the square root has already been taken for us. So we have really the square root of 4 plus 9, and that's equal to the square root of 13. So one thing I do want to mention is that if I were to now go back and do this again with our distance formula, which is a pretty straightforward formula, and switch our values around. I did x1 minus x2 and y1 minus y2. What if I did x2 minus x1 and y2 minus y1? Well, then I would have gotten 0 minus 2 instead of 2 minus 0, and I would have gotten 0 minus 3 instead of 3 minus 0. But I want you to see that the result here is very much the same, because when you square negative values, what you end up with are positives anyway. So we still get the same values here. So what I want to try now, at least with my points here, is find the distance between point A and point E and ask, how does this distance compare to the last distance we found? Well, point E, as I go back and look here, point E lied in the third quadrant. As a matter of fact, E had the coordinates -2, -3. It was the opposite of A. So if A is right 2, up 3, then I went down 2, left 3 with my particular point E here. And E, I'm going to label this -2, -3. So what I want to do now is find the distance here between these 2 points. And if you're noticing anything here, these are kind of the same triangle. So in terms of hypothesis, what do we think is going to be true about this entire distance from A to E compared to the distance from A back to the origin, and why we might think that'd be true? So writing down both of our points here, we have 2, 3, and in this case -2, -3. Let's say that our distance then is really, let's go ahead and check this out here. Using our distance formula, we could say here's our entire right triangle right here that we could use. And I can see that this bottom distance is 4 and that this leg distance is 6. But using our distance formula, which I want to do here, we're going to get this every time. So we say x2 minus x1. We'll say x2 is -2, -2 minus +2. And then y2, pardon me, is -3 minus y1 is 3. What we end up with is this right here. We get a -4 squared plus a -6 squared, which ends up giving us this expression right here where we get a 16 plus 36, which comes out to be 52. So now one thing I want to say about this, and you may not recognize this right off the bat, but there is a perfect square that goes into 52, and that perfect square, let's see here, I believe it'd be, let's see, 4 times, let's figure this out, 52 divided by 4, is that it? 4 times 13. And so what this means is that we can extract this square here, and we could say that this is 2 root 13. But one thing I want to point out here is that this distance, as you might have hypothesized, is twice as far away as A was from the origin. We can see that here, that 1 root 13 is half as big as 2 root 13. So for this last part, the distance between points B and C, I'm going to go back and check out B and C here. We say B was -4, 0, and C was 0, 0. So for this last part, we have 1, 2, 3, 4, -4, 0. This is B, -4, 0, -4, 0, and then 0, 0. So of course, this distance here is going to be 4. I mean, it's just going to come out to be 4. But why does this happen? Well, because anytime we find the distance between something that's either on the x or the y axis and the origin, it's kind of a straight line distance. So again, with our distance formula here, we have, say, x2 is -4 minus x1 is 0 squared plus y2 minus y1 squared. And what we end up with then is this square root of -4 squared, really. Because when you square 0 and add it onto this, you're not going to get anything significant. So the square root of 16, of course, is plus or minus 4. But we want to keep just the positive here because that is our distance between -4, 0 and the origin. Cheers.